coming. And more importantly, so thanks for staying. So I'm assuming you are interested in my work. So today, I'm going to share my work on a graph. We call it a NAVI-graph, so which we can use it for indoor navigation. So, my name is Junxiang. I'm a research fellow at the University of Cambridge. Okay, so where's the next one? So this is the background of my research. I would say this is my favorite work so far. So have a guess, what do you think it is? So yeah, of course, this is a graph. And this is actually a building. So yeah, it's this building. So I would say this is one of the most famous buildings in the BIM world. And if we say the 3D model is the visualization of geometric information, then the graph is the visualization of the semantic information in a building model. So this is the background of my research. And so IFC-Graph is a full representation of IFC information that's based on a property graph. So there are usually two ways of doing research. So the first way is like we have a problem and we propose a solution. So this is the traditional way, but we do have another way. So you have a new solution and you want to say, so what's the problem I can solve? And unfortunately, I'm the second type. So I already have a graph, so the problem I'm thinking, the question I'm thinking is that, okay, so what problem can I solve? So then one day, when I was looking at a subgraph, so this is a subgraph constructed from the IFC real space boundary. So this is an IFC entity, so that's connected space and all its space boundaries. So that's, as you look at this room, it has boundaries, walls, ceiling, floor, windows, doors. Yeah, so that's what the IFC real space boundary do. So connect space and all its boundary. Then I look at all those things, the orange ones you say they are space, and all other nodes you can say they are windows, doors, floors, other things. Then I look at the relationship between a space and the door, and it's giving me an idea. So I may be able to use it for indoor navigation because in this graph, as you can see, so a room is connected by a door and the door is connected to another room. So by doing this, we can construct a network for indoor pathfinding. Then my research question becomes how to use IFC-Graph in indoor pathfinding. Then I look at indoor pathfinding. So indoor pathfinding is in a wider context of indoor navigation, which have 5 parts. The indoor localization and position, so that's to find where you are in a building. Indoor navigation model, so that's basically the connectivity graph or network that you can use. And the third is algorithms you can use for indoor pathfinding. The fourth is human spatial cognition and wayfinding. So this is mainly about human part, how you find the locations, how you find the roads or the ways. Last part is indoor guidance instruction. So this is about application. So how you can get instructions, a verbal instruction or graphic instruction. But for the IFC-Graph, we can not do all the things. So we can only mainly address the second one, so indoor navigation model. Yeah. So my question be narrowed down again. So how to build a space-connected graph for indoor pathfinding from IFC-Graph? So this is a traditional indoor navigation model. So that's constructed from the conventional way. So that's used geometry computation. So that means you need to find all the space in a IFC model, building model. So you get their center, and you get all the doors or other things get center connect to them. So this way, by doing this, you can construct a connectivity graph for sure. But the thing is, it's like time consuming because we are using the geometry computation. Yep. And in the indoor navigation model, you will see all those things, door to corridor connection, a room to door, a room to window, or corridor to window. But among all those connectivities, you can see 2 types of connectivity. So the first is the horizontal connectivity. So that means you need to find out how rooms on the same floors are connected to each other. And the second one is vertical connectivity. So that means like how space on different floors are connected to each other. All right. Now, so I'm using IFC-Graph to construct this connectivity graph, and I also need to consider these 2 parts. So the first part, the horizontal connectivity graph. And the good thing is this part has been defined in IFC by using the IFC real space boundary as I introduced before. So IFC real space boundary connects a space and all the bounding elements, including doors, windows that you can pass through. And the second part, vertical connectivity, unfortunately, so this part has not been defined in IFC. So I have to extend the, I have to create a customized IFC entity, and we call it IFC real connected space. And so this entity connects IFC space and elements, and we call connecting elements such as stairs, ramps, lifts, and escalators. So by using these two connectivity graph, we can construct a building-wide connectivity graph. So the second part is about construction of the horizontal connectivity graph. Since the horizontal connectivity has been defined in IFC, and we can simply use this query. So this is a Cipher query, which is a graph query language. So this means match P is a path. A path, IFC space is connected to another thing that is through the IFC real space boundary. And the thing could be an IFC door or IFC virtual elements. So this is because in IFC, space can be connected by doors or virtual elements. Yeah. And yeah, so this is the construction of the horizontal connectivity, which is very straightforward. And the second part is a vertical connectivity graph. So this part, unfortunately, so when we are doing this paper, so this part has been done manually, but now we have developed an automatic algorithm to find out. So let's say here, so this is stair, and we can find out which two spaces a stair connects. Yeah. And the last thing is a building-wide connectivity graph. So by merging the horizontal connectivity graph and vertical connectivity graph, so we will be able to build the building-wide connectivity graph. And lastly, pathfinding by graph query. So you can just use this so embedding query from Cipher to query the shortest path between two objects. So it's either space to space or space to object. And to validate the proposed framework, so I have used this building model. So this is another famous building model in the BIM world, I would say, another one. And this building model has like 189 entities with about 150 instances. And we converted this into the IFC-Graph, which has about 200,000 nodes and about 300,000 edges. So this is like a big one. And this is the layout, the floor plan of this building, which has 5 floors. And you can say all the floor plans has a very simple I shape. You know. And the first, constructing horizontal connectivity graph. So by running this query, and we get the horizontal connectivity graph from that big one. So yeah, from this very big one, you can directly get this. But the thing is, if you have a closer look at it, and you will find, so this is not a connective graph, and there are many parts. So we have a horizontal connectivity graph for each floor. Yeah, so -1, 0, 1, 2, 3. Yeah, 5 floors. Yeah. And then constructing the vertical connectivity graph. And so by running out, doing it manually, so we find out 5 staircase and the space they are connecting, and then we can convert this into a vertical connectivity graph like this. And by combining these two graphs, so we will get this one. So this is the building-wide connectivity graph that you can use for pathfinding. And as you can see, so the graph is now a connected graph. And we run this one for pathfinding. Last is the 2 cases. The first is space to object pathfinding. So you can specify the start node or start space, and then the end is exists 91102. And by running that query, we'll get the path like this. It's a graph path. And this graph shows the sequence you need to follow to reach the exist from the space 186.482. But this is not enough. I mean, if you want to really use it in practice, you need to get like visual aid, such as lines. But in our study, so we change a little a bit. So we just use the 3D models, because like once you get the sequence, you will be able to get the ID of the instance, and you can use original IFC SPF files, and you can reconstruct the geometry. And by visualizing the geometry, you will be able to get the path you need to follow. Yeah, for this one, if you want to escape, you need to follow this one. Yeah, space, stairs, and exist. So this is like space to exist pathfinding. Another one is like you can also use it for space to space. Yeah, yeah, the same one. Yeah, you just need to divide start room and the end room, and you will be able to find the path between any two space. But we can also extend it. So if you add the facility information, such as a fire extinguisher, into graph, you will be able to find the nearest fire extinguisher. Yeah, that's right. Almost finished. Yeah, yeah. So I wanted to do a demo, but I didn't know I cannot use my computer, so I will just leave this part. So conclusion. So my study just like demonstrate it is feasible to construct a building-wide connectivity graph from IFC-Graph, and it is easier to construct, and it can enable more applications. But we do need to do more work on this. For example, we need to embed distance information into this graph, so we can enable shortest distance pathfinding, because currently the criteria we are using is called list elements. Yeah. And so this work has been extended into a journal paper, if you are interested. So it's this one. It has just been accepted and published earlier this year in February. And if you are interested in IFC-Graph, so IFC-Graph generation, IFC-Graph query, and IFC-Graph-based indoor pathfinding, so please refer to this one. And we do have a workshop, technical workshop on 17th July. If you are interested, I will cover all my work about IFC-Graph. Yeah, please come. And thank you. Any questions, any comments?